Okay, Professor Zoriana from Lviv University of Trade and Economics will talk us about hypercyclicity of symmetric composition operator. Professor Zoriana, you have about 20 minutes.
Thank you very much for opportunity to take part in this conference. I like this conference. I want to say thank you to organizers for this conference, and I want to represent my report, Hypercyclicity of Symmetric Composition Operator. I will start of classical results, also hypercyclicity criterion, symmetric function, symmetric translation operator, and I will introduce some examples, and in the second part, I introduced a new operation in the algebra of symmetric function. I will call it this operation sequence of ordering the set, and I will introduce a symmetric affine operator. So I will start definition. Let X be fresh linear space and operator T from X to X is called hypercycle if there exists a vector X was the set orbit is dense in X. Every such vector X is called hypercycle for T. The study of hypercycle operators started from classical Birkhoff's theorem in 1929. This theorem asserts that any operator TA, this is translation operator, entire functions HC on the complex plane C. Also, Birkhoff's translation we can consider as a differentiation operator. A generalization of Birkhoff's theorem was proved by Godefroy and Shapiro in 1991. They showed that if T, this non-constant entire function of exponential type on Cn, then this operator, differentiation operator, is hypercycle on the space of entire function on Cn. Theorem for entire function on Banach space compact type that are bounded on bounded subset was proved by Aaron and Bass in 1999. We will consider composition operator. Composition operator T phi is has this view for some analytic map phi from Cn to Cn. It is known that on the translation operator TA, for some A is not equal 0, is hypercycle composition operator on space of entire function on C. I want to recall the classical result in hypercyclicity theory of operators, hypercycle operators. This is a hypercyclicity criterion. Let X be a separable complete linear metric space, and T from X to X be a linear and continuous operator. Suppose there exists X0, Y0 dense subsets of X and sequence nk of positive integers and sequence of mappings, possibly non-linear, possibly not continuous Cn, so that the next conditions are fulfilled. Then operator T is hypercycle. But I didn't use this criterion for proving my result. I used another comparison criterion, and I will show this late. we need a definition of a symmetric function. A function f on L1 is called symmetric if for every x from L1, the function of the next view is called symmetric. And also we denote Pj, the sequence of polynomials is called algebraic basis in algebra of symmetric polynomials if for every symmetric polynomials P, they have the next formula. Okay. So we denote Ps of L1, the space of symmetric polynomials on L1, and we denote phi f B algebraic basis in the space of symmetric polynomials defined by the next formula. And we denote HSN, algebra of entire symmetric function on L1, which is generated by polynomials F1 and Fn. We need to introduce a new operation. We call this operation symmetric translation. So if we have xy from L1, we put x point y, this sequence, and define the operated ty is equal f of x point y. And we will say that this operation is symmetric translation, and the operator ty is symmetric translation operator. It is clear if f is symmetric function that then phi f of x point y is symmetric function under a fixed y. We have the next basic properties of symmetric translation. These properties are very convenient for proving their results. Okay. We have the next theorem. Theorem 1, let y from L1 and non-zero vector F1, Fn from Cn per cycle on algebra of entire symmetric function on L1. I want to say that this function, this algebra is finite generated by polynomial symmetric polynomials F1, Fn. The next theorem 2, let we have Fréchet algebra of symmetric entire function on L1, which are bounded on bounded subsets. The symmetric translation operator ty is hypercycle on this algebra for every y is not equal 0. This theorem, this is infinite dimensional case. This the theorem, first theorem is for finite generated algebra. Theorem, the second theorem for infinite dimensional case. I need to introduce a universal comparison principle. So let T be hypercycle operator on X and A be isomorphism of X. Then this operator is hypercycle. We will say that this operator is similar to T. If we have a composition operator, So we can introduce other operator in this form, and this operator is also composition operator. If A is composition operator with polynomial automorphism, we will say that this our operator is polynomial similar to T. So we consider operators which are similar to the translation composition TA on the space of entire function on Cn. This principle help us to prove hypercyclicity other operator Ty of a symmetric translation. So we have isomorphism Cfn is a topological isomorphism from algebra HCn to the algebra HB, a non-zero vector of Cn, and when we write the next operation get this set, we can state that this set is dense in space of entire function on Cn. And so we can state that a symmetric translation operator Ty is hypercycle on the algebra of a symmetric function which are bound. So we can see that other operator Ty is represented by other operator from universal comparison principle. So we can state that our operator Ty is hypercycle. So I want to introduce the next example when we consider the next algebraic basis G in this basis G and element of this algebraic basis, we can introduce the next formula. And gk of x point y, we can write in the following way. And we consider the operation with other operator. So we can get the next result. Why this result interesting for us? Because we can see that TA is and TJY is not commutative. This operator is not commutative. Okay. So I want to introduce the new operation. We have the next operation X. I can call ROM Y. So for X and Y, a resultant sequence of ordering the set. X, Y multiply Y, X, J multiply YJ. This is one single index in some fixed order. The next properties are very useful for us, and we have the next operation. So X mapped A romp x point y, and is a symmetric affine operator on L1, and define composition operator in the next form. So the main result, theorem 3, let a sequence from L1, such as all coordinates HA are non-zero, the symmetric affine composition operator is a hypercycle on the algebra of a symmetric function which are bounded and unbounded subsets. And they have in this theorem also infinite dimensional case. This is my reference, and thank you for attention.
Thank you very much, Professor Zoriana, for your presentation.